Okay, so next topic is an introduction to moles. Hugely important, the basis of most calculations questions in this subject. So well worth making sure you get these basics right. And by the end of this section, you should be able to do these following things, some definitions and some simple calculations that we're going to take you through. We're going to begin by looking at what a mole is. There's a very irritating song, this website, that will drive you up the wall. You might like to listen to that. But our definition of a mole is it is the number of atoms that are found in 12 grams of carbon 12. So this isotope of carbon, if you have 12 grams of it, it has this many particles, this many carbon atoms. So it's a lot, 6.02 times 10 to the power 23. And we can look at that with other substances as well. Notice I'm using the word particles. It's kind of my simplest unit. It's a little bit broad, a little bit of a hazy term. 5 moles of sodium is going to contain 5 times 6.02 times 10 to the 23 particles of sodium, which is 3.01 times 10 24 sodium atoms. So the particle in this instance is an atom, 3.01 times 10 to the 24. Next one down, 0.2 moles of carbon dioxide, 0.2 times 6.02 times 10 to the 23 is going to be equal to 0.204 times 10 to the 23 particles of carbon dioxide. And my particle in this instance, the simplest unit, is CO2, the CO2 molecules. It's 1.204 times 10 to the 23 molecules of carbon dioxide. Likewise down here, 0.1 times 6.02 times 10 to the 23 is equal to 6.02 times 10 to the 22. And in this instance, as an ionic compound, we refer to this as a formula unit. One Na plus and a Cl minus. That will become clearer when you do the bonding topics. But there are 6.02 times 10 to the 22 pairs, if you like, of NaCl within that lattice. Right, a couple of definitions: relative atomic mass and relative molecular mass. Have a look through those, make sure you understand what they mean. And here we have an equation that's going to allow us to interconvert for masses between number of moles and mass. Now, this equation's going to be really important for you. If you're doing a chemical experiment, you're weighing out some compounds, you want to work out how much you're going to get at the end, we can't be working in masses. We have to work in moles because different atoms have different weights, and it's the number of atoms that turns out is the important piece. So we're going to practice a little bit using this relationship. This is a relationship we used on the slide 2 back. And so how many moles is 5 grams of lithium? Well, we're just going to use this relationship here. Number of moles is mass, mass is 5. Mass of 1 mole, if you look at the definitions, lithium, can be a bit lazy, just use it as 7, and you can work that out and you'll get your answer. What's the mass of 10 moles of water? Well, this time we have to do a little bit of rearranging, because what we've got is the number of moles is equal to the mass, which we don't know, divided by the mass of 1 mole of water. Water H2O, so that's 2 plus 16, which makes 18. So my mass is going to be 180 grams. How many molecules are there in 3 moles of carbon dioxide? So 3 moles of carbon dioxide, 3 times 6.02 times 10 to the 23. That's going to be the number of molecules. How many oxygen atoms are there in 40 grams of calcium carbonate? So here I've got to get to moles first, so I'm going to do mass divided by mass of 1 mole. Calcium carbonate CaCO3, molecular mass there's going to be 100, so that's 0.4, and then I need to do 0.4 times 6.02 times 10 to the 23 to see how many calcium carbonate formula units I've got. But the little trick here is it's saying how many oxygen atoms, and if calcium carbonate is CaCO3, each of them has 3 oxygens in it. So I'm going to have to multiply each of those particles by 3 to get the number of oxygens that are tucked away in there. Right, percentage composition tells us how much of an element there is within a compound, and it talks about fluorides in toothpaste, nitrogen in fertilizers as an example here. So we could think, well, if I've got a bag of this stuff, which one has the most nitrogen in it? And simply to work it out, you should just do the percentages. So again, I'm not going to use particularly accurate atomic masses, but this one's got 14, got 2 ends in there, over the mass of the whole thing. The whole thing weighs 12, 16, 14, 15, 16, 32, like that, and express that as a percentage, and you'll find out how much nitrogen there is in there. And for the ammonium nitrate, again, I've got 2 ends in it as a percentage of the mass of the whole thing. So I've got my 28 plus 4 plus 3 16s, which are 48. And if I express that as a percentage, you can see which one has the most nitrogen in it. Another term to consider is empirical formula. Empirical formula is the simplest ratio of the atoms within a formula. So a molecular formula is what it actually is. Often we can cancel things down and we end up with this empirical formula. You can see some examples there. And empirical formulae can be worked out, very common exam question. Using some information, we can work out what an empirical formula is, what the simplest ratio is. And then by knowing, if we're told the actual molecular mass, we can work out the molecular formula from that. So, as an example on the last slide you can have a look at. Here's another example. You've got a compound that's got 56% phosphorus in it. So I'm going to pretend, instead of it saying percent, I'm going to say, let's say I've got 100 grams. So the mass of my phosphorus is 56.2, the mass of 1 mole of that is 30.97, and then my oxygen, I've got 43.8 divided by 16, and working those out, 56.2, this is 1.81, this is 2.73. So I want to look at this, well, what's the ratio? I've got to have whole numbers in my ratio, so I divide by the smallest number. So if I divide both by 1.81, and I find that my ratio becomes 1 to 1.51. Now, I can't have half of an oxygen atom in my formula, so what I'm going to do is then scale this up. So I'm going to have a 2 to 3 ratio. So my empirical formula is P2O3. I've got information on the molecular weight, so I can ask myself, well, how heavy is that? Well, the mass of the empirical formula is 2 times phosphorus, which was 30.97, plus 48 for the 3 oxygens. Oops. So my mass of the empirical formula is 109.94. How many lots of this do I need to get the molecular weight? Well, hopefully you can see it's twice the amount. So my actual molecular formula must be P4O6. Right, another variation of the same thing. We're throwing up the information that's going to tell us the amounts of the atoms in the final compound, and have to work out the formula. So I've got 2.3 grams of sodium. Again, being lazy, not looking up the proper atomic masses. There we go. Makes 3.1 grams of an oxide. So that oxide contains sodium and oxygen. So it means that the amount of oxygen that is in there must be that difference, which is 0.8. So that was our sodium, that's the oxygen that gave the final mass of the oxide. So how much oxygen is combined? Well, it's 0.8 divided by 16, which is going to be 0.05. What's my ratio? Divide by the lowest, so divide by 0.05. That means I've got 2 to 1. The formula is Na2O. And knowing my combining powers as well as I do, that's going to be correct. Right, so that's what you needed to know. The differences. Check through that, and we'll be moving on from that to some more complicated calculations in the next few sections.